Okay, let's kick things off here. It might be a few people still coming in, but the start of this is just going to kind of be talking about the protocols. The tutorials are going to be a little later on. So this is session 4. Welcome back. This is our final instructional session. The next one is kind of an open session where you can come with any issues you're having, or if you've got a project in mind you wanted to get some more ideas for, you can bring that and we can kind of talk shop with your local team and figure out a path forward if that's what you want to do. But today's presentation is going to be on networking and communications. So on Sysmac PLCs, the NJ and NX series are very network capable PLCs. So out of the box, they all have, at a bare minimum, Ethernet and EtherCAT on them. Now, everything we're going to be doing today is going to be out of the Ethernet port. And the agenda will consist of a quick overview of what exactly we support as far as protocols go. And then we're going to dive into primarily the specifics of Ethernet IP, and then we're going to do some of the implementation of Ethernet IP. So this will be a live demo done by me. I have the hardware with me that we'll be interfacing with. I'll show you how to do it in Sysmac Studio. Now, obviously, without having the hardware in front of you, you can make the code, but it's not going to do anything. I will be distributing this after the class, so we'll have lots of examples in it. There's also an example project included in the student material that has a lot of this stuff in it as well. So after Ethernet IP, we'll go over OPC-UA. And since our PLC is an OPC-UA server, it is very easy to set up. So that's primarily just going to walk through enabling it in the PLC. And then I'm going to use a piece of software on my computer that will let us browse the OPC-UA server, and we can see all the tags that we set up in the PLC. After that will be classic Modbus TCP. We'll do a quick client demo and a quick server demo. Then we'll wrap things up with kind of a quick summary of everything we did and use cases for those protocols. And usually we're done this one fairly early, and we'll have a good question period at the end. You might have some questions about your application and what protocols might suit it best that we might have time to dive into. So, so some of the communication options, and we're going to talk NJ series. So the NJ line of controllers will take CJ cards. Those of you that don't know, the CJ PLCs are older line of controllers, but they were able to talk on a lot of legacy protocols, and we can still use those cards on our NJs if the need arises. So CAN Open, CompoNet, DeviceNet, ProfiNet, Profibus, and Protocol Macro are all specific to the NJ. So they're all fairly old protocols, but we can do them with the NJ. And what Protocol Macro is essentially a serial card that has, out of the box, these protocols listed in it here. But you also can write your own protocols with it. So I don't think it's listed here. No, so there are a couple Modbus RTU protocol macro libraries kicking around if you wanted to use it. But so those are NJ specific communication options. Now the NJ and NX all support these. Some of them are certain models. So the NX1P2, for example, the shoebox PLC can't do OPC-UA or SQL. Okay, so EtherCAT, Ethernet IP, everything out of the box. MQTT function block libraries are on our website. Same Modbus TCP, function block libraries built into Sysmac. Modbus RTU, same thing. IO link, we'll need an actual card to do IO link. OPC-UA and SQL are on certain models. And then Ethernet and serial, just kind of raw ASCII communication. Socket services, it's commonly called in the Ethernet world. They can all do those out of the box, every model. So now we'll step into Ethernet IP. I'm sure most of you are familiar with it or have at least heard of it. And Ethernet IP I think it is the most common protocol currently in the North American market. And it is commonly used for a high-level communication protocol. So PLC to HMI, PLC to PLC is a very common use case. But really, it's pretty flexible. It's pretty versatile. And we're seeing it, we're seeing temperature controllers now with Ethernet IP on them. We're seeing, drives even that don't require real-time control. We're seeing Ethernet IP on servos. So we're seeing it on the IO network, motion networks. We're seeing it everywhere now. Super common, and we're very compliant with Ethernet IP. So third party Omron, we can talk to pretty much anything over Ethernet IP. Now, there are basically two flavors of Ethernet IP. One of them is called implicit messaging. So commonly called a tag data link. If you're reading on the SIP standard, that's what they refer to it as. But basically, this is where we set up a link between our PLC and an adapter class device. So say a VFD or a smart camera, something like that. And we tell it we want to go after a certain tag set, and we want to update that data at a certain RPI, or requested packet interval. And our PLC behind the scenes is going to get that data at that requested packet interval. It's going to monitor the health of that connection. It's going to report to us if there's a timeout or a connection loss. But it's essentially a set it and forget it kind of connection with the device. It gets that data at every requested packet interval, and we use it, and we're aware that it might be 10 milliseconds old, but if that doesn't matter, Ethernet IP is often a good protocol in many situations. So that's implicit messaging. Explicit messaging on Ethernet IP is something that is done that's much more similar to a Modbus message. So you've probably heard of a class, instance, and attribute when you're going after a specific parameter in a device. So when you're using explicit messaging, this is commonly used for a data point on a device that isn't included in your implicit data, but you might need to modify it from time to time. So for example, if you had a VFD, your current limit might not be included in your implicit connection, but you might need to adjust your current limit based on what you're powering, what you're driving, kind of thing. So that would be kind of a use case for an explicit message. And we do this. This is a much more manual process. So this is something that we need to initiate in logic, and we need to send, and we need to monitor on our own in logic. So a much more manual process, but it's also something that you don't generally do over and over again at a regular interval. Sometimes you do, there are use cases for it, but that's explicit messaging in a nutshell. Now, the first exercise that we are going to do is explicit message a third-party PLC by tag name. So we have a few options when it comes to explicit messaging. So like I mentioned before, when it's a device like an inverter, you're commonly given a data map in class, instance, and attribute type parameters. And I've got an example here of that, something that we're going to be Modbus messaging, but this does SIP messaging as well. So this is an adapter class device. It's an intelligent power supply that Omron makes. So here's our class, here is our instance, and here is our attribute. So using those three values, we can drill down to these parameters. Now, when we're talking to another scanner class device, PLCs are often scanner class devices, they will support something called tag-based explicit messaging. And that will let us ask for data by tag name. So in this little snippet here, I have a screenshot from a third-party PLC, and it has a real variable in it called myRealVar. It has a value of 123.45, and I'm going to make a new Sysmac project, And we are going to first set up an explicit message with this PLC, and we are going to ask for this data by tag name. So if you want to play along, you can. Like I said, your simulator is nothing's really going to work when you're simulating this, but if you want the practice of setting this up, you can. I'm going to distribute the program after the class as well. So give me a second here to open up a new Sysmac project. I have a lot open on my computer right now. I apologize. It's taken a little bit of time to wake up here. There we go. So the PLC that I'm going to be using for all of this is an NX102 1220. So it's a version of NX102 that has SQL capabilities built into it. We could do an entire session on the SQL aspect of it. It could get quite in depth, so we're just going to stick to kind of the easier, more common protocols on it. Looks like I've still got the spinning wheel here, so please be patient. There we go. NX102, I have a 1220, and I think I am on a pretty old firmware actually, but that doesn't matter. So I'll create my project. And I'm just going to make a routine called tag-based explicit. And in our toolbox for Ethernet IP explicit messaging, we have a lot of different options. If we just type SIP, that's going to tell us all of the options that we have for explicit messaging. And there's a use case for each one of these. But the SIP UCMM are the most common. So UCMM send is what you would use if you were doing class instance attribute. UCMM read or UCMM write is what you would use if you had a tag that you wanted to go after by tag name. So I'm going to read that tag. So I'll use the UCMM read block. I'll zoom in a bit here for you guys. Okay, so this is our function block, SIP UCMM read. This is what we use for tag-based explicit messaging. And there are not too many parameters on it, but there's one called the route path. That's a string variable. And this is something that is common to SIP messaging on every single platform. If you've dealt with SIP messaging, you've probably had to set up a route path. It's very well outlined in the SIP standard, but to make our life a little easier, we can always press F1 if we don't know exactly what the route path means. And we have examples down here of route paths. That there's a massive section in the SIP standard on route paths. Now, if this were an Omron PLC, it would be one thing, but because this is a third-party PLC, they have slightly different route path requirements on their end. So to get out of our PLC is O2 / and then the address of the destination device. So that's an R manual. Now the last portion of the route path is going to be in the target device's manual. So I'm going to save you guys the hassle of viewing all of that, because I've done that work already and I know what the route path is. So I'm just going to copy and paste that. So O2 sends this out, the first port of our PLC, and it sends it to a PLC that has the address of .2. Then this is specific to their controller, but essentially this gets it directly to their processor. Different devices will have different route paths, and yeah, we could have an entire session on route paths, but for now, that is the route path. I've tested it. Next, we have our timeout. Obviously, we don't want to sit there and wait too long for this, so I usually use a value of 10. Now, the source data, this is the source variable name. So in our third-party PLC, if you remember from the presentation, it's called myRealVar. So we are just going to type that tag name. So myRealVar. And it will ask for myRealVar from the other PLC when that message gets there. The size is just 1. So if that was an array and we wanted to pull 15 elements from it, we could ask for 15 and we could specify the starting index as the source data or the tag name. Now the destination data is where that data is going. Now, one thing about the tag-based explicit message that you need to be careful with is it is the only situation in explicit messaging where the data types matter. So if this were the class instance attribute type explicit message, you could grab a floating point from your target device and you could bring it into an array of Booleans, and it would be none the wiser. You would have to make sense of it still, but the block would execute and it would execute without errors. Because we know this is a real, we need to bring it into a real, and our PLC will verify that these two data types match. Now, they can be structures, they can be arrays, they can be a number of things. Word of caution, Booleans generally have issues, but every other data type is okay in most cases. But I'll make a tag here. I'll call this myRealVar. I'll call it the same name, and I'll make sure it's the same data type, real. So myRealVar, this is a constant. This is a string constant. I just hard-coded a string here in single quotations. MyRealVar is a variable in my PLC, and we can look at I like to put a tag under the receive size just so I know how many bytes came across. So I'm going to send this to my PLC now. My IP address is 250.1. I can test the connection. It says test OK, so it sees it. So I'll go online. Now I do have an IO card on my rack, so I'm just going to do a quick compare and merge before I transfer it. Otherwise, I'll get a configuration error that's going to be kind of bugging me all the time. Now I can do what's called a synchronize. So this will compare my project with the project on my PLC, and anything that's different, it's going to prompt me that it needs to be transferred to it. And in this case, because this is a fresh project, it's just wanting to transfer everything. But if I had only modified one program, one line of one program, then I could just transfer that program. And in a large project, that can speed things up. Now, while that's synchronizing, just kind of a snapshot of what this network currently looks like. So my PLC is 250.1. I've got intelligent power supply on 250.20. I've got a third-party PLC on 250.2. We aren't going to be using this IO-Link master. And then we have a smart camera on 250.40. So that's that'll be our implicit connection that we'll do next. So it's synchronized successfully, and now I can go to my logic, and the value of my real var should be 123.45. So when I execute this block, it reported success, and it's grabbed that value of 123.45, and it's brought it into my real variable that I made in my PLC. And the size, it's reported as 4 bytes, which is correct. That's the size in bytes, not to be confused with this size parameter here. So that's the number of elements you want to read. And if you mouse over it, the tooltip should clarify that. So that's an explicit message by tag name. So I was reading in this example, but I could write to it just as easily using the SIP UCMM send, or write, I believe it is. Yeah, SIP UCMM write would do the same thing, but in reverse. I would send it a value. So any questions on explicit messaging? If anyone's trying to recreate this on their end and you want me to pause here so you can finish some parameters or something, let me know. I don't mind. Okay. So that was a third-party PLC tag name based explicit message. Now we're going to do something called an implicit connection, and we're going to be using a smart camera. So this is a microscan camera. We've rebranded them. Omron purchased Microscan, and it's now the Omron F440 and V430. We have a number of different cameras in the series, but the one in particular that I have is an older one, and it's still considered a microscan camera. So for an implicit connection, we are going to be opening up a section of Sysmac that we've opened up before when we were checking the size of variables in the third class. So if we go to Tools, Ethernet IP Connection Settings, that's how we open up the interface to set up an implicit connection. Now I have 2 ports, and I can set up implicit connections out either port. So I'm going to choose the port that the camera is connected to, which is 250.1, the top port here. It's port 1. And now it brings me to this window here. So we have 2 sections here. So we have the tag sets on the top, and we have the connections on the bottom. So we need tag sets created, and in our connections, we decide what device those tag sets will be connected to. And then we also, in the right-hand side, have our toolbox, and we have a target device window. So I'm going to add a device. I just click the plus sign there. The first thing I'll do is add that device, and we enter the IP address of that device, which is 250.40. And under the model name, these are all of the EDS files that I have installed in Sysmac Studio. If I needed to add a third-party EDS file, I'll show you guys how to after this here, but I'm looking for the Microhawk MV40, which is this one here. That's the camera I have connected, and there's only one revision. So I'll click Add once I have that selected. Now, if I needed to add an EDS file, say I've got a third-party VFD, something like that, I can right-click in here, and I can choose Display EDS Library. And these are all of the EDS files that I have installed. So lots of third-party ones in there. And if I wanted to add a new one, I would just click on install. I would navigate to that EDS file. I don't think I have any in here in the student material, no. But you would just click on the EDS file, install it, and then you will now have that as an option in your toolbox when you're setting up a target device. Now, once we have our target device listed here in our toolbox, we can click the plus sign in our connections tab, and it will create a connection. And from this dropdown, we'll choose target devices that we've created. Now, there's only one of them, of course. So that is our smart camera. And all of this information here now is going to be interacting with the EDS file for the device. So if we look at the target variables, we only have one option on this camera, and that's 102, instance 102. And it knows from the EDS file that that is 320 bytes in size. And for our output instance, we only have 114 as an option. And again, the EDS file told us that that's 320 bytes in size. Now, we haven't set up any variables for Ethernet IP yet. That's why we don't have any options in originator variables. So we could make an array of 320 bytes if we wanted to. And if you guys want to play along, that's what I suggest you do, because I have a structure I'm going to be using. So we know it's 320 bytes. So we can kind of pause here and create that variable now. For mine, I am going to be using a structure. I have a structure for this camera that I've been using for years. So I'm just going to copy and paste from a different project that has that structure. You guys obviously won't be able to do that, but if you want to make an array of 320 bytes, it will let you add that to your data link. So I'm just going to paste this from a different project. And now I have input assembly 102. I have a structure that outlines all 320 bytes of it. And then I have my output assembly, and again, a structure that outlines all 320 bytes of it. So we can use structures directly with our implicit connection, and that will make our life a lot easier. If you could imagine parsing all of this out of a byte array, it would be quite a headache. So in our global variables, and if you guys are playing along, you can do this as well. You just won't have that data type option. So I'm going to call this camera input and camera output. And the data type that I select won't be an option for you, but you could put byte and then in square brackets 320, and that will let you use this with that connection. But I'm going to use that input assembly 102 structure for my input, and for my output, I'm going to use output assembly 114. And now the network publish column, I've been saying we'll come back to this quite a bit in some of the other sessions, but this is where we assign an implicit connection variable. So by default, do not publish means that we do not share this tag with anything. It's internal to our PLC. When a tag becomes publish only, that exposes it for OPC-UA as well as tag-based explicit messaging from another PLC to our PLC. Input and output are what we'll be using for implicit messages. So input is obviously going to be used on our input assembly, and output is going to be used on our output assembly tag. So camera output is output, camera input is input. Now this is from the perspective of the PLC. This sometimes comes up when you're setting these things up. You're looking at one manufacturer's documentation and it's written from their perspective, but the camera's output is our input. So occasionally you do cross paths in that way, and you can simply just switch these, reset your tags and test it the other way around if you had to. But now that I've defined these as input and output network variables, now when I go back to my Ethernet IP settings, which is just a tab up at the top, Now, when I go to my tag set window, I can click on registration all, and it's going to go through my global variables, and it's going to look for any tag that I assigned as an input or an output. It's found my input tag is camera input and my output tag is camera output. So I will register those tags, and you can see the size is 320. When we click on this drop down here, what we are doing is we are looking for a tag that we have registered that is an input variable that's 320 bytes in size. And we only have one of those, which is our camera input. Same thing on the output. So if we were off by 1 byte when we made our structure and we click this drop down, it wouldn't suggest camera input because it would be a size mismatch. Any questions on what we've done so far?
Yeah, Stuart. And this may be something for maybe at the end of the session, but I have had troubles with using structures for inputs, outputs because of size mismatches.
Yep.
And is there any way of dealing with those? As an example, I had a Ethernet IP connection with 128 bytes, and I made a structure of it to make it easier, like you did with this camera. And the structure came back as 132 bytes, and it gave me a mismatch, even though if you add them up manually, it comes to 128 bytes. Now, I know that some of the structure have some padding here and there. There's some warnings out there about using structures in the padding that's in there, but like in the background, but I don't know if there is a way to deal with that.
So was your structure was smaller, or your structure was larger than what your instance was? Is that
Yes,
what's
correct.
happening? Yeah. When you were creating it in your structures window here, did you select the user offset type?
Yes, I did.
Yeah. Okay, because if you've selected the user offset type, I mean, it should be fairly easy to figure out based on your byte offset where you went wrong, basically. Like here we've got 292 is our last byte, and this is a 28 byte long string, so we know that 320 should be our total, right?
Yes. And the funny thing is, like when I went through it, it showed as 128 bytes, but then when you rebuilt the project, it switched to 132, which is kind of odd, but there's something I guess that I've struggled with in the past using the structures as a Ethernet IP tag set.
Interesting. If you want to send me that project, I'm kind of curious myself.
Yeah, I can do that.
Yeah, I mean just over Teams audio, I'm not sure how much I could help you with, but
No, that's fair.
I personally haven't experienced that. I mean, I've missized them, but I've always been able to figure out where they were missized.
Yeah.
So yeah, let's take that one offline and let's revisit it. Sure. Okay, so I have my input and output tags. Their structures, they're sized according to my EDS file and the communication manual of this camera. So I'm going to go online now, and because I both created new tags and I set up an Ethernet IP connection, I'm going to do a full-blown synchronize here. And this will get faster and faster as we're just changing little bits and pieces of the project when we use synchronize. Okay. Now I'm going to transfer, now that those tags have been transferred to my controller and those structures, I'm going to execute transfer to controller here down at the bottom. And this is something that can be done online. We don't have to go to program mode to make changes to Ethernet IP. We can do this all as essentially online edits when we're setting up and modifying Ethernet IP stuff. So it's convenient. So that's been transferred to the controller. And a good indication that it's working is, for starters, I don't have a red light down here on the error light. But a quick way to check your connection is from our Ethernet IP device list here. If we right click on the port that it's going out of, we can select monitor. And if this was a red circle, we would have a problem, and it would also give us an error code that we can look up to see what the problem is. But we've got all sorts of detailed information here, from dropped packets to, tag sets and their consumers, that sort of thing, connected time, unconnected time. So lots of troubleshooting information in there. If the connection wasn't a success, then we would also have an error, and we could open up the troubleshooter, and it would tell us that the data link wasn't working, and it would tell us what's going on with it. So, but now that we've established that connection, we can go down to, I'm just going to do the view watch tab page table, and I can look at this data live. So I'm just going to trigger the camera. So that'll be my camera output. It should have a trigger bit in it, which is right there, trigger. So flipping that bit, there's a little flash on the camera beside me. I know you guys can't see it, but I can bring it over and show you. So hopefully I can do this on one screen. But every time this bit passes from false to true, so I'll put my hand in front of it, take a picture. It's kind of hard with one monitor here, but so that's the camera, that's my hand. It's just whited out the entire screen. And when I do this again, you should be able to see. Now you can see the circuit board behind it. So the connection's good, everything's functional. And that's how we would set up an implicit connection with that device. So this is an input and an output connection. Some devices are input only, some devices are output only. Based on the EDS file, we'll have allowable RPIs. We'll have support for point-to-point or multicast connections. But yeah, that's an implicit connection and how we set it up. You don't have to use structures. You don't even need the EDS file. Omron has something called a generic Ethernet device EDS file that you can install, and that will let you pretty much connect to any instance, any size, and it will skip over all of the major and minor mismatches, stuff like that. They're commonly called a generic Ethernet device if you're familiar with another common platform. So yeah, that's a quick demo of an implicit connection. Any questions on that so far? If I were to lose this connection, and I'll just unplug my camera here, you'll see pretty quick my red error light went on down here at the bottom right. There's a red light blinking on my PLC as well. And if I go up to my troubleshooter now, it will tell me, bring it over to the other window here, it will tell me there's a minor fault coming from Ethernet IP. It's a tag data link timeout, and it's giving me the error code here. But generally, tag data link timeout means you can't reach the device. Since I unplugged mine, that would make sense. So it gives you the yeah, there's some attached troubleshooting information you can look at as well. Now, Ethernet IP is self-healing. So if I plug this camera back in and I wait about 10 seconds, it's going to clear that error. It's going to resume the connection. Not all protocols are self-healing like this. So the camera takes a minute to boot up. I'm not going to make you guys wait, but you will notice shortly here that the run light switches from red to green again, because that connection has been reestablished. The data I'm getting is going to be refreshed, and then it's like it's like it never happened essentially. So okay, so that's an implicit connection. Now we'll quickly talk about OPC-UA. So this is a protocol that's been around for quite a long time now. It's commonly used in SCADA communications. Most of the major SCADA players have an OPC client built into them. Now, our PLC is a server, so it's not a client. We couldn't talk to another OPC device if we wanted to. We're a server, we sit there and wait for requests, and we serve those requests. Being that we're a server, it's actually very easy to set up OPC. Get the project open here again. So I'm going to go offline with my PLC. And some of you might have noticed in our Multi-View Explorer, we have OPC-UA settings. And if we expand that, we have our server settings. All we need to do is just flip this to use. And we've now enabled our OPC server in our PLC. If we want to record execution logs, we can check off record, and it will actually keep a diagnostic log in the SD card of the PLC that you can reference in the future for troubleshooting and traceability kind of thing. And with that enabled, all we have to do is go online and transfer that to the PLC. And if you haven't done it before, it's going to ask you to restart the controller. So it's prompted us that we need to reset the PLC. That's fine. We can do it right from Sysmac Studio. I'll flip the controller to program mode. Then I'll select reset controller. We'll disconnect from it automatically. And in about 20 seconds, should be back up and running. And then we'll connect again, and OPC-UA will be enabled on our controller. Now, OPC-UA is very straightforward to set up a basic unsecured implementation of it like we're doing here today. I'm on a fairly old firmware, but our new firmware supports a lot of security settings for OPC-UA. So we can do anything from username and password based authentication to security certificates that need to match what the client has. We also support encryption for it. So it's gotten quite secure over the years, and we've stayed up to speed with it. So I'm back online with my PLC. My OPC-UA server is in use. And now when I right click on it, I've got a bunch of new options here. So there's the server certificate, there's client authentication. We go to security settings, and to make things easy today, I'm going to allow an anonymous login and no security policy. But we can sign and encrypt up to 256 SHA type encryption. So we'll transfer that to the controller. And now we have the server status that we can look at. And you can see our server is being used, it's running. This is our endpoint. So if you set up OPC on SCADA, you will need an endpoint URL. And that's what ours looks like. It's just opc.tcp and then our IP address and the port that we selected. We don't have any clients currently connected, but I do have a piece of software called UA Expert, which is just a quick OPC client that will let us look at OPC-UA servers and kind of see what they have available on them. So we'll come back to that. In the global variables, I'm just going to do an online edit here. I'm going to add some tags in an online edit for my OPC-UA server. So I'll call this my uint. I'm going to set it to publish only, and that puts it on OPC-UA. I'll add a couple of those. I'll make one a real. We'll throw a couple of those on there. We can have many variables on OPC-UA. I'll send this online edit. So now I've added some global variables with the publish only attribute enabled on them. And now when I connect with UA Expert, I'm just going to add a server. It's called NXPLC. And that URL that we were looking at earlier is right here in our endpoint URL. So opc.tcp, the IP address of our PLC, port 4840. We don't have any security policies enabled, just to keep things simple. We're going to do an anonymous login. We're going to select OK. And now, if you've ever had to work with, say, an address-based protocol and a third-party HMI, you need to export variables and import variables and retag and reshuffle variables just to get everything in line. But with OPC-UA, you are looking at tag names. You're working with them directly. So we have pulled the PLC here, and it's a little small. I can't zoom in, sorry, but we've pulled the PLC, and we've retrieved every global variable that's exposed on OPC-UA, and they're listed right here. Okay. Now this is just a browsing tool. If this were SCADA software, I could select this from the SCADA software and tie it to a level gauge, for example, on my screen, and really save that middle step. There are lots of other advantages to OPC-UA. It's another one we could probably do a whole class on, but a simple implementation is very easy to set up, and it's a big time saver when you're developing a SCADA system primarily. So any questions on OPC-UA? Now, I'll also point out the server status that we were looking at before. If I update that now, you can see I have one connected client and one user. So this will constantly update. I believe we have system variables that we can look at these with as well. So that is a quick demo of OPC-UA. Like I said, the PLC portion of it is very simple to set up. The client does most of the work. So that was the demo we just did. Now Modbus TCP, I live in Alberta and we love Modbus here. So Modbus TCP has been around for a very long time and is surprisingly common out there still to this day, despite how old it is. We have on the network here an S8VKX power supply, which supports Modbus TCP. So in our communication manual for this power supply, I'll go to the Modbus section. And this is going to be pretty consistent with Modbus devices in general. If you set one up, you'll recognize pretty much everything we're looking at here. So the Modbus TCP section is going to outline some function codes that it supports. So this power supply supports function 3, which is reading multiple registers. It supports function 6, which is actually an operation command. So that's just what we use to reset some of the peak hold values. And then we can also write multiple registers if we wanted to set the IP address and some of the Ethernet settings on it. But we are just going to go after the output voltage and some of the basic parameters on this with Modbus TCP. So we'll come back to this, but we'll be using function 3 for our Modbus. Now, Modbus TCP and the Omron PLCs, they do have, by default, in the toolbox, Modbus function blocks to be a Modbus client. So I'm just going to add a Modbus section for this. And if we look at the toolbox and we type mod, we'll get essentially the default Modbus instructions that come with Sysmac. So we've got Modbus RTU, we've got Modbus TCP. But one thing that it doesn't have is a Modbus TCP server in it. So I like to use a library that we have available on the internet for Modbus TCP server, but it also has Modbus TCP client functions in it as well. So I believe this was included with the student materials if you wanted to import this into your Sysmac project. So I'm going to go to Library, Show References, and I'll add a library. And it was in the student material, PLC libraries, Modbus TCP, and there's MTCP NJNX library. So this will work on any NJ and any NX PLC, and it does client and server functions for Modbus. It might flash you a warning about a firmware version or something like that. You can ignore it, but if we expand that library that we just imported, you can see we have functions now for the client. So function 3, function 6, function 5, etc. But we also have this server block down at the bottom. So we'll do server next. We'll just do client for this one. So I'm going to go to my Modbus program. And the first block, we're going to do client first. So the first block will be MTCP client connect. It would just be a socket TCP client connect you do first if you were using the built-in Modbus functions. We'll give it a name. Now, the IP address is the IP address of the device you want to talk to. So if you remember from our network overview, our power supply is .20. So we'll hard code a string with single quotations, 192.168.250.20. The port is almost always 502 with Modbus, but we could do a different port if needed. Oh, sorry, I think that's actually unsigned integer. Yep, unsigned integer 502. And connect, this is the Boolean that we're actually going to turn on or off when we want to connect to this device. So I will say start MTCP connection. Now, when we have established a connection with our target device, let me zoom in a bit here for you guys. When we have established a connection, this output will become true. So I'm just going to put a coil on that rung just so it's a little easier to see. So that's our rung, essentially. We do output two other variables that are very important here. So our socket variable, this is what all of our functions are going to use. This essentially tells it how to route the traffic. So we'll call this our MTCP socket. And then the socket status is optional, but it's nice to know. This will tell us if our connection's established, if we're in a timeout wait scenario, something like that. Okay. So once we have established our connection and we are connected, I'm going to add another rung below it here. So I'm going to reference that connection established bit. And we will use function 3, because that was, if you remember from the manual, one of the supported function codes of this drive was function 3, multiple register read. Now the registers themselves, we go to the register address list and you can see they start at 0 and they go up to 8. And they are, for the most part, 2 bytes in length, couple double integers, couple integers, that kind of thing. So we'll grab index 1 and we'll take 1 through 5, I think. That should be good. So at index 1, address 1, we'll start with. Our register address is a word. So it's going to be word pound 0001. The socket variable is going to be the socket that our client connect block used up here. So that's MTCP socket in our case. Paste it. Unit ID, almost always going to be 255. Now the register quantity, we said we'll grab 5. So that's an unsigned integer. And send request will actually be what initiates that function 3. So then O3 send. Now the data that it reads is going to get sent to whatever is in this register output here. So it is a specified data type of 128 words. It's an array. So I'll call this FN03 rec data. And whatever we get from our function 3 will come back into our FN03 rec data variable. So just give this function block a name and then we can test it out. So I'll go online. Transfer to the controller. Okay, so when it comes time to test, the first thing we'll do is turn on our client connect block. So that's just this Boolean here. If we double click on it, we can turn it on. You can do it programmatically as well. And it's indicated that the connection was a success. And our socket status down here has changed to established. Now I'm going to execute this function 3 command, which is going to go after register address 1 through register address 6. It's a quantity of 5. And we do that by flipping the send request bit true. And if everything was okay and we got data back, this block command OK output will be true. And now I can look at the contents of FN03 rec data, and that should contain the values that we were polling. So I'll go to my watch tab page table, since it's an array, and I'll look at FN03 rec data. And there you can see the first 5, and we'll change the view from hex to decimal. So 2440, there's a divide by setup on this one. So that's actually 24.4 volts. That's telling me the output voltage is, and that's outlined in the manual. I'm just going to turn that potentiometer down a notch on the power supply just so we can get some new data in that parameter. Okay, so I just walked it down to 23.7. So if I execute this block again, I should see 2370 on there now. There it is, 2370, so 23.7 volts. So Modbus, unlike Ethernet IP, we get the data in arrays of either words or bytes, and we need to make sense of them, essentially. Parse it out, convert it, whatever the need might be. You can use structures and use an instruction called ARY byte 2. ARY byte 2. So if you ever need to convert a chunk of data in a byte array into anything else, a structure, a string, an array of elementary data types, this is what you would use. So you could have a structure for this power supply, and you could convert these words to bytes quite easily. then you could just map that directly to a structure variable, and it would take care of all the parsing and everything for you. So, but for this, we'll just, it's kind of a proof of concept here. So there's our data. It was successful. It responded. So that's Modbus TCP, quick tutorial on it. Does anybody have any questions on Modbus TCP, client at least? Okay, server is much easier. I'm just going to go offline for that one. I'll make a new program for Modbus server. And back in our toolbox under the library that we imported, there's an MTCP server block. We can just drag and drop that on the rung. And I like to have the ability to toggle it. So I'll put a bit here, server starts. And now we only have 2 input registers on this, or sorry, 2 input variables for this. So our registers, which when we mouse over, we can see is an array of words for registers. And when we mouse over the coils, we can see it's an array of Booleans. And these are going to be the data that we respond to. So if it was a function 3 that we were getting, which is read multiple registers, we will take register 1 is going to be register 1 in this array. So we'll reply according to the data address in this array. So I'll just call this my MTCP serve regs. Oh, little typo there. It's okay. MTCP serve coils. Now, when somebody connects to us, we will turn on this connected output. So you might want to know when somebody's connected to you before you start your machine or something like that. So I'll call this client connected. And then we have a few information type tags down here. So we can check the status of our connection. We can check the IP address of the client that connected to us, and we can also check the port that the client is using. So they're always going to connect to our port 502, but they might use a different port, and that'll just tell us the port. It's really not that important, but okay. So I'll send this to the PLC now. And when we start this server, it's going to open up port 502 on our PLC, and it will allow a client to connect to our PLC. Now, I prefer to use a PC-based client when I'm testing things out. So I'll be using a piece of software for Modbus on my PC, and that's also easier for you guys to see what's going on as well. So I'll start the server by flipping this bit. Now, nothing is connected to us, which is why our connected output is false, and our server status is indicating that the port is closed. So nothing is trying to connect to us. So I've got some Modbus client software here, and if I go to connect, and I put in the IP address of my PLC and the port that I opened up, which is 502, And you'll see in the background, as soon as I click OK here, it's going to turn on the output to this rung as soon as that connection is made. There it goes. So now I've got a connection. It's reporting that 192.168.250.123 has connected to it. That's the IP address of my laptop. And we're using port 51,704. It just picks a port. It really doesn't matter. So that worked. Now we can, using our watch tab page again, we can modify these registers here. So those are registers. There are 1,024 of them. So if I just put some data in there, 1, 2, 3, 4, 4, 3, 2, 1, 7, 6, 2, 39. Now I should see these come back on my Modbus client server or software, sorry. So there's 1, 2, 3, 4, 4, 3, 2, 1, 7, 6, 2, 39. So just kind of a quick confirmation that we are serving the data, we're serving it where it's supposed to go. And we're using function 3 for the holding registers. If we wanted to go after the coils, which is function 1, they're all false right now because I haven't set any data in them. But if I go to the server coils and I just kind of flip a couple of them, I'll flip every other one. We'll see that now in our Modbus software. We've got the 101010 pattern. So any questions on Modbus server capabilities in the PLC? Okay. Well, I will disconnect, and you'll see behind me as soon as I do that, it's also going to indicate a disconnected client. So it updates pretty quick. And it's often good to know when you do have comms with a Modbus device, even as a server. Okay, so kind of to wrap up what we covered today, OPC-UA, if you use SCADA, you probably support it. Very simple, enable it, publish your tags, and you're finished. The vast majority of the work is done on the client end, but it's a very convenient way. With the latest firmware on our PLCs, not even the latest, I think this is something we implemented a year or two ago, but we'll actually support structures over OPC-UA now. So you can even use structures on OPC-UA now. We've kept pretty up to speed with it. For Ethernet IP, data links are what we set up and they're handled automatically. That's what we did with the camera, okay? The class instance attribute or tag name type explicit messaging, we have to do that through logic. And I did mention that there could be a use case for this. Now, all PLCs are limited on how many implicit connections that they can have going at one time. Now, there's no limit to how many explicit connections you can have going at one time. You are limited on how many sockets you have open at a time. But in the case of a power supply like we had there, if you had, 150 of these in your plant, you probably don't want to set up implicit connections with every one of them since you're just looking to, read the max current from time to time. If you get an update once a minute, that's not a big deal. But if you wanted to save on implicit connections, because we are limited, every PLC is limited on implicit connections, that could be a use case for explicit messaging, but it won't be fast, that's for sure. You'll have to kind of set up a messaging carousel and cycle through them all. But Modbus TCP, most people are familiar with it. We do client and server. Pretty simple to implement. The function block library was included in the student material, so you have it. You can use it. There's documentation online for it if you're having any issues. And you also always have this video that you can reference as well. So we are done. We've got about 15 minutes left. So if anyone has any questions or you have anything you're curious how you would do, now's a good time where I could demo something or we could talk a little bit more in depth about it.
Yeah, on the Modbus server, how does the user know the register and the coil addresses?
Yeah, so they so basically in let me fire this back up. So we start at 1. Modbus generally starts at 1. And in our array, when we are asked for register 1 on, say, let's say it's 30,001 or 40,001, we treat them the same in the PLC. We are going to respond to a request for register 1 with array index 1.
Okay.
Yeah.
So we just have to populate the registers and the coil data. That would
Exactly. Yeah. Yeah.
Okay.
And so coil number 123 is array index 123. So we, ignore the first, like the 10,000, 20,000, 30,000, 40,000 type thing. We'll take care of appending that in the background. But yeah, it's
Right.
1 to 1, 5 is 5. Yeah.
That's pretty sharp.
Yep. And occasionally, I mean, the need does arise as well to have multiple clients talking to a Modbus server, and it's not too hard to figure out where inside this function block we specify port 502. So what I've done in the past is basically duplicated this and just changed the port number to 503, and you can run as many of these as you want. Really, you're just limited by sockets at that point, which we've got plenty of. So. Yeah, any other questions or something kind of specific you're wondering how to do on any of these protocols?
Yeah, so Stuart, it's Tim. I'm
Hey, Tim.
looking at doing a project, and basically what is happening, they have a network, they have a PLC within that network, and then there's going to be some equipment that's going to be installed, new equipment, and that's going to have its own router basically with VPN capability.
Okay.
So we're trying to figure out to set up an Ethernet IP implicit messaging between the two PLCs, and one is outside of that router and one is inside. So basically you have to go through like a firewall or whatever. So is there a way to do that? Or is that basically you'd manage that with like a link layer 3 sort of IP translations on ports?
So when I've had to pass implicit connection data through, it's mainly just been enabling the ports through your VPN. If the device supports point-to-point, you're going to have better luck with that than multicast, because they'll generally block multicast by default. But that setup's generally done in the switching hardware itself, in your network infrastructure.
Right.
So if you wanted to set up VNC on an HMI, right, you'd have to forward that port all the way through your network, make sure that protocol and that port is allowed through, and it can route it properly. So yeah, it's really just a matter of setting up port 44818 on all of your switches.
Okay.
And making sure that traffic can get through. You will probably run into a lot of lost packets. It's not uncommon. So, I mean, I wouldn't have super high expectations of your RPI. 50 milliseconds is probably unrealistic. But you
Yeah,
can
no,
set, you
this-
can
this
set
is
your
not-
API, right?
Yeah, it's not super, doesn't
Yes.
need to be super speed, right? Like it's more of a sort of a SCADA type connection where it doesn't have to be instant. It's just kind of monitoring and changing
Okay.
values that are, process set points basically that would change, and it doesn't have to be, it can take a second to update. It's not a big deal.
Yeah. Okay. Yeah. So
So-
you can choose a slower RPI, and you can set your timeout to,
Yeah.
quite a long time if you wanted to, right? But so
Yeah.
you'll probably have to play with that just so you don't get so many timeout errors. But yeah, I have done it. It's doable. But yeah, you will lose a lot of packets along the way, I find.
Yeah.
But
that's fair, but
yeah.
Okay. Sounds good. Appreciate that.
I guess while I do have you guys here, I have been kind of maintaining an example program over the last couple of years here. So this has been distributed to all of you before the session. It's in the student material. This is a good reference point in the future. So the first time you go to make a PID loop, for example, it can be a little daunting. So there's a PID loop in this program that is configured, ready to go. It even has simulated feedback, so you can simulate your PLC, see how everything takes effect and how it affects the PID. But it also has all of these starting values in it that some people, it's a big time saver. They're commented, it tells you what they do. All the starting values you need. So I don't know, Tim, have you done a PID in Sysmac before?
No, I haven't done it in Sysmac before. I did it in the CES, CJ a little
Okay.
bit, but
Okay.
yeah.
Yeah, there's just a lot of starting parameters that can throw you off and cause funny errors. So just a good reference for PIDs here. And again, it's got Modbus TCP client examples. It has the libraries included in it. So the Modbus library and that analog sim library. So TCP client, TCP server. So everything we did today, this has got a commented configured example ready to go. For Ethernet IP, I know I hope I didn't scare too many people with that route path. It's kind of something we can't avoid, and it happens on every single platform. But we've got an example of a route path here for a different PLC. I think I don't want to name competitors here, but a common manufacturer's route path is here as an example. This will hopefully save you some time. And then an Omron route path too, if you had to go between an Omron PLC. And then the class instance attribute. We didn't cover that, but it's got an example of how to do it with class instance attribute. So scanner class device to an adapter class device generally is going to be the SIP UCMM send, which needs class instance attribute. And bit extraction, we did a little bit on day 3. But this just kind of gives an example of how to do it with some kind of visual feedback of how you do it. There's the memory addressing has already been done for you, so you can kind of see how it all comes into play. But keep that example program in your back pocket, and this is going to pretty much cover everything we've done over these sessions and more. And it's a good reference point in the future. These are things that can slow you down when you're working on a project if you haven't done it before. So we still have about 10 minutes. If you'd like to jump off, you are more than welcome to jump off. Next session is essentially what we're doing now. If you have something specific you want to bring up or you have a project you're thinking of taking on, we can kind of provide some guidance and support on it. So I'll hang on the call for another 10 minutes here if you've got anything to chat about. Tim, if you wanted to stay on, we can look at that structure.
Yeah, I gotta go find that project. It's been a while. So we'll maybe do that another time when you have some time. Yeah.
Sounds good. Okay, well, for everyone else, thank you for attending, and we'll hopefully see some of you next session.
Thanks a lot.
Bye.